Hi, welcome back. We're in the last lecture, in the last segment, where I'm just giving you an overview of the main topics and issues that were covered in the course. In this last segment, we'll talk about what we covered in the last few lectures, which are how to deal with non-normal distributions and nonlinear models. So we first dealt with that with categorical outcome variables. So throughout most of the course, when we were doing correlation, regression, multiple regression, t-tests, and ANOVA, in all of those procedures, we were assuming a continuous, normally distributed outcome variable. So like a ratio or interval variable as our outcome variable, y in regression, or the dependent variable in t-tests and ANOVA. What happens if you have a categorical outcome variable? Well, in those cases, we use chi-square and logistic regression. So if all of your variables are categorical, both your outcome and your predictors, then you can do chi-square tests. So we did the chi-square goodness of fit and the chi-square test of independence. Then we looked at binary logistic regression. So we had a binary and categorical outcome variable with a whole set of predictors that didn't have to be categorical. They could be a combination of categorical and continuous. Then we did logistic regression. Then we talked a little bit more about the idea of non-normal distributions. So we got a little bit more precise about how to detect whether something's normal or not normal. Remember, the simplest way is to just eyeball histograms and look for extreme skew, extreme kurtosis, or look for outliers, and look at scatter plots to see if we have linear relations. You could also do those QQ plots and look to see if you have a linear function in your QQ plot or not. If you don't have normal distributions, sometimes you can apply that quick fix strategy and just apply a transformation to your outcome variable. And remember, the common transformations were square root, logarithmic, and inverse. And if they were negatively skewed, we just reflect and do those same transformations. Now, of course, sometimes we could not apply a quick fix. We just couldn't get past the violations of assumptions. So that's when we finally turned to nonparametric procedures, such as Wilcoxon's ranking method, Mann-Whitney's U. Those were the two that I illustrated in lecture. But remember, there are nonparametric procedures that correspond to all the parametric procedures that we covered in this course. So again, if you're interested in those, I suggest an entire course on nonparametric statistics. And then finally, we dealt with nonlinear models. So throughout the course, we assumed that there was a linear relationship between a set of predictors and that outcome variable y, but that might not be the case. You might have very complex functions relating x, or a set of predictors of x, to y. In that case, you use this more flexible mathematical framework, the generalized linear model, which allows you to test any sort of function, not just linear. And remember, it does that by adding in that key component, the link function. And I showed you just a few examples of that, the binomial or binary logistic regression example, then the extension of that into the multinomial logistic regression, and then finally a Poisson regression, because that's another common nonlinear model. But that generalized linear model allows you to move beyond the general linear model and test for more complex regression models.